we developed the grand canonical ensemble. Right. And now we're going to use it. So in grand canonical ensemble, what do we know? That the probabilities of being in any given state are e to the power minus beta ei minus mu n I, okay, divided by z, where z is again just the sum over all those, so the summation over all the different states. And you have the contribution of e to the minus beta ei minus mu n I. Great. How we relate this to the thermodynamic representation? So we know that the grand canonical potential, which is F minus U minus ds minus mu n, and this psi equals minus 1 over beta log of z. Right. Now the grand canonical ensemble, the energy is not constant, but we have different states, and the states are defined by the energy at the state and the number of particles in the state. Right. So those are the two important quantities. We developed the canonical ensemble. So remember again, we started this, not this class, but statistical mechanics with the microcanonical ensemble, and it was difficult to solve. Then we eased the condition of a constant energy, and by easing this condition, we managed to obtain something which is much more easier to solve. Okay, so for the canonical case, we only have this. The energy is not constant, okay, but we have different energies. Then fluctuations of energies, they permit us, okay, to treat the system in much simpler way, basically by using this representation. The same goes for the grand canonical ensemble. So by allowing the system to have a different number of particles, so we ease the condition of a constant n, which sometimes we say, well, it's if we have to satisfy this very specific constant number of particles, it can be combinatorially difficult to solve the problem. So what grand canonical ensemble does, so it's not a more physically relevant case, but it also technically easier to solve grand canonical ensemble where you can have different number of particles than solving a canonical ensemble where you have this constraint of constant number of particles in the system. Okay. Now we're going to use this grand canonical ensemble specifically for the case of quantum gases liquid. And we start with a very simple example of, we have three different energetic states. So this is our energy. And we have epsilon 1, and we have epsilon 2, and we have epsilon 3. Okay. We have a temperature for the system. And we treat fermions. Now, the thing about fermions, and we can maybe also add here non-interacting. When I say non-interacting, I mean that the particles do not affect each other. So if you remember in the Debye model, all the particles were somehow affecting each other. There was a very big potential that we expanded around the minima. Now in this example, we only have fermions. And since we are trying to do the grand canonical ensemble, we don't have a constant number of particles. And I'm trying to say, well, the particles are interacting. Okay, so usually fermions, like electrons, so electrons repel each other because they have an electric charge, and the two charges with this repel each other. Now we completely omit this from our discussion, and we say, well, there is no interaction, but it's a trick. It's a lie. Why? Because fermions always affect each other, and this interaction, it's actually has some sort of an infinite range, if you want to if you want to treat it like that. What is the interaction between different fermions?
The Pauli exclusion.
The Pauli exclusion principle. Okay. So for fermions, we have the Pauli exclusion principle. Which says the following: any two fermions cannot occupy exactly the same state, right? So what I mean by that, I mean that the moment I put a particle, one fermion, with a spin up in the state epsilon 1, no other fermion with spin up, okay, is allowed. So if I try to put another one over here, it's a forbidden state, and I simply cannot do this. Right? This is interaction. Okay? So any system that have fermions, it's a system where the particles do interact because they feel each other, right? So, and they cannot occupy exactly the same states. All right. So I want to describe the system, and what I mean by describing in statistical physics, it's always the same, is if I know the partition function, I can obtain the grand canonical potential. The moment that I have grand canonical potential, by taking a specific derivatives, I obtain whatever I want, right? So the goal is always to compute somehow the partition function. Now, I already told you, and it's the same for grand canonical ensemble, that we have only one prescription of how we obtain the partition function. We need to write the energy, or whatever stands inside over here, as a sum of independent quantities. So far, we describe it as a sum of energies of independent particles. Sometimes the particles were real particles, sometimes the energies were effective energies, like for example, the case of the polymer, and sometimes there were no particles, but quasi-particles, like phonons, when the positions were not the locations of a specific particle, but the description of a mode or vibration of a solid. But it always those two conditions. Energy is a sum of different energies, and those different energies have to be uncorrelated and do not affect each other. Now, when you look on the case of quantum gases, even for this very simplistic model, we have three different energetic levels. We have fermions that can occupy this level. Now, usually, the thinking is the energy is the energy of what? The energy is the energy of the different particles that I have inside my system, right? So I look on all the different particles that I have inside the system, and I count all those particles and all their energies. Some of them are going to have spin up, some of them are going to have spin down. I'm sorry. And the total energy is an energy of the particles. All right, this is good. But the second part is I need that all the different particles and their energies should be independent. But this is not the case for fermions, right? Because the fermions, they always affect each other. The moment I have one single particle sitting in one specific place, no other particle can occupy this exact state. This means that the particles always affecting each other, and I cannot treat them as independent quantities, right? So this method, and this is the only method that I have to describe energy as a sum plus some independence that leads to factorization of the partition function, is going to fail. Right? I cannot describe this system as a sum of the energy of the different particles. Right? What I can do what I can do is to notice that instead of, and this is the beauty of the grand canonical ensemble, and specifically this part, is that I can treat the system not as a sum of the energies of different particles, but the occupation of different energetic sites, right? So let us look on this system in the following perspective. So the total energy, I'm going to do the following thing. It is epsilon 1, okay, multiplied by I of epsilon 1. What is I epsilon 1? It is 1 if epsilon 1 is occupied, and it's 0 if epsilon 1 or otherwise. Basically, it's a Heaviside theta function or an indicator function, if you know it's from probability, that says, well, if the site is occupied, this is 1. If it's unoccupied, it's 0. Okay? So the total energy is epsilon 1, I epsilon 1, plus epsilon 2, I epsilon 2, plus epsilon 3, I epsilon 3. So I managed to write the energy of the system as a sum of energies, but those energies are the sums not of the different particles, but of the different states. Yes?
Don't we lose something here? Because there can be two fermions in the same energy.
Great. So let's write it down as I up, and up. And I can have plus epsilon 1 I down epsilon 1 plus epsilon 2 I down epsilon 2 plus epsilon 3 I down epsilon 3. Right? So this is the degeneracy. Right? So I'm assuming that the energy is independent if I have spin up or spin down. Okay. But in order to write the total energy, I'm saying, well, I'm now trying to write the energy not as the sum of the different particles, but the sum of the states. Now, if the state is occupied, it's going to contribute the energy that is associated with the state. If the state is not occupied, it's going to contribute 0. Now, the thing is, because all the different the states are independent, one state couldn't care less about all the others. Right? So if the state is occupied, yeah, of course, the particle cannot penetrate the state, and maybe it will go to some other places, but we don't care about that, because we managed to write the energy as a sum of the different energies of the different states, and all those states are independent of each other. The state is either occupied and it's not occupied. Okay? If it's not occupied, it's not going to affect the possibility or the other state at all. Right? So when we write this down and I treat it state by state, this is why I have specifically for up states, so states with spin up and states with spin down. Okay? When I treat it as a summation of the energy of the different states, it works. Right? I cannot do this for different particles, but I can do this for different states. Okay. Now that I have this, I can go backwards to my definition of the partition function and use the idea of factorization. Right? So the energy is a sum of energies, and all the different energies, those quantities, are independent of each other. State 2 doesn't care about state 3, state 3 doesn't care about state 1. So I can use factorization. And this means that Z which is the sum over all the different possibilities e to the minus beta ei minus mu ni, is going to be composed as a factorization of z1 up multiplied by z1 down multiplied by z2 up multiplied by z2 down multiplied by z3 up multiplied by z3 down. Because I could write, or I can write energy as a sum, I can write the partition function as a multiplication of different partition functions. And the only thing that I now have to treat is the partition functions of each single state. The states are independent, they have specific partition functions, treat them independently, multiply them, and you're done. Right? So the energies, this is the extension of this idea. Energy is the key to everything, specifically when you can manage to write it down as a sum of independent values. Right. So let us see what are all those different z's that we have written down, what they look like. So what is z1? z1 up. So we know that there are only two possibilities. Right? So either it's unoccupied or it's occupied. So when it's not occupied, we have e to the power minus beta, and here we have this expression. So this is the state when the system or the state is unoccupied. When it's unoccupied, its energy is 0. Minus mu. When it's unoccupied, the number of particles of the state is 0. Okay. So this is state number 1 of energy E1 with spin up. Alright, what is state number 2? We have only two states. So it's e to the power minus beta. When it's occupied, the energy of the state is epsilon 1 minus mu multiplied by 1. Right. That's it. There is no other states. It's not an infinite sum, no nothing. It's either occupied or it's unoccupied. Okay? So we have here, this is e to the power minus beta 0, so it's simply 1, plus e to the power minus beta epsilon 1 minus mu. Okay. The same thing goes for z1 down. Right? Why? Because the energy is independent of the spin. So when this state with epsilon 1 and spin down is unoccupied, it is e to the power minus beta 0 minus mu multiplied by 0 plus e to the power minus beta epsilon 1 minus mu multiplied by 1, which is 1 plus e to the power minus beta epsilon 1 minus mu. We do the same thing for all the other two energies. We do the same for epsilon 2, and we do the same for epsilon 3. Now, notice that z1 up and z1 down has exactly the same form. Now, why? Because the energies is independent of the spin. If they were dependent on the spin, it would be a different matter. So basically, the degeneracy of the energy due to the spin, we can say that z1 up equals to z1 down, and the same will happen to z2 up is going to be equals to z2 down, and z3 up is going to be equal to z3 down. So in total, z is z1 up to the power 2, z2 up to the power 2, z3 up to the power 2, or we can forget about up or down. We have z1, z2, and z3 to the power 2. And if we had other states of the spin, so this is the degeneracy that enters into the calculation. So if we had possible spins which are +1, +2, -1, -2, it's still a fermion. We could do that. It would give us, instead of 2, 4, because there will be 4 degenerate states. All right, so what happens? So we know Z1 up, Z1 down. What happens to Z2 and Z3? The calculation goes exactly as for Z1. So Z2 is e to the power minus beta. If it's unoccupied, so the energy is 0, minus mu multiplied by 0, plus e to the power minus beta, epsilon 2 minus mu multiplied by 1. So it is e to the power it's just 1, plus e to the power minus beta, epsilon 2 minus mu. The same goes for Z3. So what is Z3? It is e to the minus beta, 0 minus mu multiplied by 0, plus e to the power minus beta, epsilon 2 minus mu multiplied by 1, which is 1 plus e to the power minus beta, epsilon 2 minus mu. So for the fermions, with the Pauli exclusion principle, with the very strong interactions due to Pauli exclusion principle, we still can calculate the partition function, but the trick we use is that we do not use factorization for particles, we use factorization for states, and this gives us 1 plus e to the power minus beta, epsilon 1 minus mu, multiplied by 1 plus e to the power minus beta, epsilon 2 minus mu, and 1 plus e to the power, e to the minus beta, epsilon 3 minus mu, all of this to the power 2. This is our partition function. The moment that we know the partition function, everything is possible. You want to compute something? Great. Okay? Calculate psi, which is -1 over beta log of z. Remember that psi is u minus es minus mu n. Okay. And here you go. For example, you want to compute the entropy. S is going to be minus dou psi to dou t. You want to compute the average number of particles. It's going to be minus dou psi to d mu. But the truth is that we don't, well, the forms are simple, because you know that what is u, function of, you know that this is a Legendre transformation of u. You take a derivative, the thermodynamical potential you calculate it because you know the partition function, everything is known. But it's actually even simpler than that. Why it's simpler than that? Because you see, the idea of statistical mechanics and this factorization is that the moment you manage to perform factorization, you can treat each system in your factorization scheme, which is Z1 up or Z1 down or Z2 up or Z3 down, as an independent system. Right? So this factorization, this one, appeared only because the energy is additive and it's independent. The moment it's independent, the partition function displays an independent system. So we can treat this combined system of 3 states as 3 independent systems altogether. So for example, we can calculate the occupation probability of each state. Now, why do we need the occupation probability of each state? For example, if we want to compute the average number of particles. Okay. So instead of taking this derivative, right? Instead of taking this derivative, we can do the following thing. N, mean value of the number of particles in the system. All right? So what is n? It's an average of n1 plus n2 plus n3, right? Because the average number of particles is the number of particles at state 1, number of particles at state 2, and number of particles of state 3. The average of a sum is always the sum of the averages. So it is n1 average plus n2 average plus n3 average. Now, how we compute this? So I don't want to go to this derivative. I want to compute separately n1 and n2 and n3. And actually, it's a little bit more than that. Why? Because I have a degeneracy. So it is n1 up, n2 up, and n3 up. And then I have plus n1 down, plus n2 down, plus n3 down. So here I have plus, so it's n1 up, plus n1 down, plus n2 down, and this is up, plus n3, what is this? This is down, and this is up. 6 different states, treat each of them separately. How to compute n1 up or n2 down? This is simple because this is a single state, independent of everybody else, and it has only 2 possibilities. Either it's occupied or it's unoccupied. So Fi, oh I'm sorry, Ni up, okay, so this is the number of particles in state with epsilon I and spin up. So it is either 0 multiplied by the probability of being 0, but I don't care about this probability. So let's write it down. F up I hat plus 1 when the system is occupied, multiplied by the occupation probability. So Fi up occupation probability. Which means the probability that state with epsilon I and spin up is occupied. Okay. How do I know what is this Fi? From the definition, right? Fi up, it is e to the power minus beta. It's occupied, so it's epsilon I minus mu. I don't have ni over here because ni can be either 0 or 1. It's one single state, one particle per state, divided by zi up, which is e to the power minus beta epsilon 1 minus mu divided by what is zi up. It is 1 plus e to the power minus beta epsilon 1 minus mu. Those are the occupation probabilities. We can also say the occupation fraction. Okay. Why it's an occupation fraction? Because actually the average number of particles per state equals exactly the occupation probability. Okay. Now since it's either occupied or unoccupied, the fraction, it's the probability. Right. So this Fi on this specific expression is the occupation fraction of any given state with epsilon I. Now notice that it's independent of the spin, which is reasonable because spin is a degeneracy, so we don't really care about this. Okay. Great, so we have now the probability of being at, not being at state, but the probability of state I to be occupied. Okay. So the average number is, let's take this formula and put it inside all the different n1 up, n2 down, n3 up, and whatever that we have over here. So what do we obtain? We obtain e to the power minus beta epsilon 1 minus mu divided by 1 plus e to the power minus beta epsilon 1 minus mu. Now, n1 up and n1 down, they contribute exactly the same probability. So we simply put 2 over here. The same goes for the second state. Plus e to the power minus beta epsilon 2 minus mu divided by 1 plus e to the power minus beta epsilon 2 minus mu. And again we have 2 from the contribution of n2 up and n2 down. So the same degeneracy. Okay. And the third state is e plus e to the power minus beta epsilon 3 minus mu divided by 1 plus e to the power minus beta epsilon 3 minus mu. And we have the degeneracy 2. Okay. So even if I don't remember this formula, and I don't remember all those thermodynamical classes that I took last year, and whatever I reminded you at the beginning of this semester, I can always, or I must remember, at least the probability properties, and I can compute everything by noticing that it's really simple to compute the probabilities of the states to be occupied or unoccupied. Now, the same goes for anything else. If I want to compute the entropy, I can take the derivative of the long function, or I can say, well, S is minus k Boltzmann sum over I fi log fi. And I can perform the summation. If I want to compute the energy, the average energy, I can take the derivative of U equals the derivative of psi, or to compute this guy from here. I know psi, and I can obtain S, and I can obtain N, and then I can substitute it inside this formula. Or I can say, well, U, it's a sum of I, EI, whatever you choose. Usually I prefer to use those formulas and this formula over here, but it's actually have a nice flavor to it to use the Legendre transformation and remembering all the different connections. If you know what are the variables that define U, it's really easy to remember what are the different derivatives that come from the Legendre transformation of the energy, because the grand canonical potential is the Legendre transformation of the energy. Now, in all of those formulas, what is important, at least for the energy, is this Fi. This is Fi up. So this is the occupation probability of each state. Now, because of the different states are independent, this I have shown you due to the factorization of a partition function, I treat each state differently. It has a different partition function, and each of them have a different occupation probability, and everything is completely defined by this occupation probability. So let us spend 5 minutes till the end of the class and study a little bit the properties of this occupation probability. Now, maybe before I will do that, now notice something interesting about this n. So the average number of particles inside the system depends on two quantities. It depends on, so n is a function of, well, the energies, let's assume that they are constant, and we have two parameters, beta and mu, right? So I take the different energies, I say that they are constant no matter what I do to the system. This is my model, epsilon 1, epsilon 2, epsilon 3. But the parameters that I can control somehow are the beta and mu. Now, since beta is 1 over k Boltzmann T, it's simply n is a function of the temperature and the chemical potential. And my two parameters, control parameters, are temperature and chemical potential. Now, usually, it's much more easier to do something else. It's hard to control. So temperature I know how to control. I can heat it up, the system, or cool it down a little bit. So I know how to control temperature. The chemical potential is a little bit harder task to achieve. It's much more easier to do something else. Okay. It's easier to control the number or the average number of particles inside the system. And actually, in some cases, I can assume the following. I can assume that the average number of particles, it's not simply some number, but it's actually constant. The number of particles is constant. Because I've studied, but why then you used all this grand canonical perspective? Well, because I couldn't solve this Fermi gas, okay, the simple example, without the grand canonical representation. So I have performed the grand canonical representation, obtained the quantity of average number of particles, and then I set this n as a constant. I set n as a constant. Now, I have an equation, which is a general function. It looks like this. It's a function of two parameters, t and mu. And I say, well, this n is constant, and my parameters are now t, and this constant value that I can control. Okay. This makes the chemical potential a function of what? Temperature and n. Now, we started with the description when I had two parameters. Remember how I developed the grand canonical representation ensemble? I developed an equation which relates the average number of particles to temperature and chemical potential. And then I stand on my head and say, forget about this. Because I don't know how to control the chemical potential of the system. But I now know how it depends on the temperature and the average number of particles. I can control this guy. I can prevent from particles to escape or coming inside the system. So I can control this. I can control the temperature by controlling the heat. Right? So I now can express the chemical potential as a function of temperature and n. And this chemical potential enters in this important quantity, F. So I but I can study the properties of the occupation probability by means of this chemical potential that is much more important quantity or uncontrollable quantity, and I only can control it by controlling the temperature and the average number of particles. Okay. So we are going to study the properties of the occupation fraction. Remember that we are looking on it as a function of the epsilon, or beta and mu. But mu is in some sense is not a constant. Mu, we'll treat it in the future as a function of the temperature and the mean number of particles inside the system. All right. So I want to study Fi. Forget about Fi, which is, let's call it f of epsilon. Epsilon can be epsilon 1, epsilon 2, epsilon 3, which is e to the power minus beta epsilon minus mu divided by 1 plus e to the power minus beta epsilon minus mu. And it's easier to write it down because when I take this part from the numerator and I push it inside the denominator, and I have 1 over 1 plus e to the power beta epsilon minus mu. Okay, now I can plot this f of epsilon as a function of epsilon divided by mu. Why epsilon divided by mu? Well, if you wish, I can take it out and I have 1 plus e to the power beta mu epsilon divided by mu minus 1. So if beta and epsilon are constant, the only variable that I have, which depends on epsilon, is epsilon divided by mu. Now, this is actually unitless because the units of epsilon are joules, or some energetic units, and the same are the units of mu. Okay, so what we know, when epsilon divided by mu equals exactly 1, we have 0 over here, so we have 1 divided by 1 plus 1. So no matter what beta is and what mu is, f of epsilon always has this value of 1/2 when epsilon divided by mu equals 1. Okay, now, when epsilon divided by mu goes to plus infinity, this is a large number, extremely large. So epsilon to some large number is extremely large number. So 1 divided by very large number is 0. So we have a decay towards 0 for large epsilon divided by mu. Okay. Now our epsilons are energetic levels, and we have all the energies are defined with respect to energy equals 0. So epsilon attains only positive numbers. Okay. So when epsilon divided by mu goes to extremely small number or negative number, okay, where this guy goes?
It's linear.
In some sense linear, but what I'm trying to say that it's going to be, so we have to cross this 1/2, it has to raise, and it will start to saturate towards smaller and smaller numbers of epsilon. Now, I cannot say that I only know that this is a negative number, but actually towards epsilon goes to 0, to which number it converges is going to be dependent on beta mu. If beta mu is very small, this number is going to be just a little bit above 1/2. But if it's beta divided by mu, it's very large, right? So I'm going to have a convergence towards 1. So what we have is, we have 1 over here, and beta mu is very large number. We're going to have something that looks like this. Okay. And if beta mu is a small number, we're going to have something which is almost flat. Now, in the limit when beta mu is actually almost infinity, okay, what I mean by beta mu, so if mu is constant, beta, remember beta is 1 over k Boltzmann t, so beta mu is mu divided by k Boltzmann t. So when this relation is satisfied, when t goes to 0, so when t goes to 0, we have a very sharp transition between the state is going to be occupied if epsilon is smaller than mu. Okay. And it's going to be not occupied when epsilon is larger than mu. So here, epsilon larger than mu. Here, epsilon is smaller than mu. So what we see that in low temperature regimes, mu plays the role of a level that separates all the energetic states that they are occupied, and here the probability is 1. So these states are definitely, with any epsilon that's below mu, any state in the limit of small temperatures is going to be occupied. And all the states that they have energies that are larger than mu are going to be unoccupied. So mu, energetic level that separates unoccupied states from occupied states. In the t goes to 0 limit. Now, because it's a very important level, right? It has a name, and it's termed the Fermi level. The Fermi level or energy. Right. So, and we see that in the regime of low temperatures, the only thing that is important for any given energetic state is that it's either below the Fermi energy or above the Fermi energy. Okay? And this Fermi energy is exactly what? The chemical potential. And the chemical potential, as we have seen, is going to be dependent on the temperature of the system and the number of particles that we have inside the system. Okay? Important to remember. In the other regime, when beta mu is smaller than 1, so when this happens, because beta is 1 over k Boltzmann T, so this appears when the temperature is what? It's going to be infinite. Just a second. What happens over here? So this line is almost a flat line. It's almost never decays. It has a small decay, but it's almost never decays. What it means that in the limit of large temperatures, all the different states are equally probable. So it can be either occupied or not occupied. You don't really care. And this is the intuition about large temperatures, high temperatures. Why? High temperatures, temperature is the kinetic energy, 1/2 mv squared, average. So when I have a lot of kinetic energy, high temperatures, I can be anywhere that I like. So all the different states are equally probable to be occupied. Okay, so this is the big difference. And the Fermi level, Fermi energy, we don't really care about it anymore. Yes?
You speak only in a 2 level.
No.
So it's not in half, it's 1 over the single energies.
No. It's an occupation probability of a single level. I don't care about everybody else.
But how the probability works if you have 5 states, so have in large...
So that epsilon, so give me a state. This is a specific state. This is not the distribution. Give me a state, epsilon, and I will tell you what's the probability to be occupied and what's the probability to be unoccupied. It's not the distribution with respect to epsilon. It's the value of the probability of a state with a given epsilon to be occupied. The integral doesn't have to be equals to 1. It's not a probability density of epsilon.
But if you have 5 states, you can have 5 states with 50%...
Why not? Because what? The number of particles is conserved? No. And this is the answer to your question. if I had a conservation of particles, you're completely right, but this is a hard question to answer, and I don't know the answer. This is why somebody very smart invented the grand canonical ensemble. Because I don't want to go into the combinatorics of saying, if this is occupied, this is not occupied, and this is occupied, and I have to compute all the different combinatorial variations. I don't care. That's the beauty of this thing. Right, so next lecture we're going to treat the Fermi gas completely, and by the way, this function is very, very useful to anybody who studying AI, because in the computer science department they call it a sigmoid function. Maybe we'll talk about it later. See you on Sunday.